Alright, so today we will start chapter 3. So chapter 3 is all about processes. um, what is a process, what are the characteristics in a particular process, and why is it important, what are the parameters available in a process, and um, how processes communicate each other, and what are the available mechanisms inside the operating system to manage multiple processes, because today's operating systems are multiprocessing, multitasking, because a particular user can run many applications, so each application will have many processes running. So processes has to be managed efficiently and effectively in order to quickly respond to the user's requests or user's preferences, and also without crashing the system. The operating system should run all the necessary processes and facilitate the users. So these are the topics that we will cover in this chapter. So first we will see what is a process and what are the characteristics and what are the parameters available in a process, and how a process can be scheduled based on different mechanisms inside the operating system, and how a process works inside an operating system. And then normally the available processes will communicate each other and then do a particular task. So processes can be divided into two categories, that is independent processes and uh, shared processes. So in that particular aspect we have certain processes communicating each other. So we'll see what are the available mechanisms for interprocess communication, we call it as IPC, and what are the client server communication techniques available inside the operating system when there are multiple processes running inside. And these are the objectives. So operating system can execute different types of programs. Some will work as batch systems, so that means a number of functions will be executed as a sequence in a given particular application. So another variety is time shared systems, so that means users can run multiple programs. So each of these programs should execute properly, and then without a delay the users should be facilitated. So in the textbook that I have uploaded, you will see term job and process is used for a process interchangeably. So a process is a program in execution that we have seen in chapter 1 as well. So the passive state becomes an active state. We call it as a process. So when a program gets executed, we call it as a process. So a process has many characteristics and parameters available. It has a program counter, a stack, a data section, and many more. So we will see these parameters in detail. So this is how a process looks like when we consider the main characteristics in a process. There's a stack, heap, data section, and a text section. So in the stack of a process we have the temporary data. So that means a stack is a data structure where you can push parameters inside and pop parameters outside. So a stack will be used to store temporary data in a process. Then we have a data section to store the global variables, because when a process initiates, if there are any global variables required, it copies the values of the global variables into the process. And there's a heap. So the importance of the heap is to store the code for a process, so that will be dynamically allocated, because in a particular given time a particular process may require a particular amount of memory, but time to time the amount of memory will vary, so it should be dynamic. So the heap is going to manage the memory allocation, that is dynamic memory allocation. And also the program or the process code will be stored in the text area. So that is how a process is initiated and manages by a operating system. So process will be in different states inside the operating system. When a program becomes a process, we call it as a new process, and then it will be available for execution. So when a process is executing and using the processor, the state changes to running. So running means a particular process is at the moment using the CPU or the processor for execution. And sometimes when that particular process requires input output operations, then it will be taken out from the CPU or the processor, and then it will be waiting until the particular event or input output operation completes. So the ready state is the state that it waits for a CPU or a free processor to execute its instruction. And when a particular process finishes its execution, it will terminate. So these are the important 5 states for a process. So this can be shown in a diagram as well. So this is the diagram. So when a program becomes a process, it becomes a new process. So then it's in the new state, and then it becomes ready when a process enters into the ready queue. So what is this ready queue? You will learn about this later on as well. So a CPU can execute only a single process at any given time. So there will be multiple processes which are ready to use the processor. So how does this operating system manage these multiple processes using a ready queue? So when a program or application starts its execution, the necessary processes will be put into the ready queue. So the ready queue will be managed by the operating system such a way that the CPU will start the execution in the ready queue without any delay. So when the process is executing, then the state becomes running. That means it is using the CPU. So sometimes we can save the file, or we can take a printout, or we can copy certain information from one file to another file. So in that type of a event, so those are input output operations. So then the CPU will stop the execution of that process and put into a waiting state. That means that particular process is waiting until that particular input output operation completes. On completion of that particular input output operation, it will be put back again into the ready queue. So this particular circle from ready to running, running to waiting, and again for the ready queue, so this particular cycle may happen several times for a process until it completes. So when a process completes its execution, it will be terminated. So those are the available 5 states for a process. So how does a process save its state? By using a process control block. So each process will have a PCB, or process control block. Why is it important? Because we have to save the process state when a process change from one state to another state, and when a particular process stops its execution, then we have to store where it stopped and where we need to start again. So then we need the program counter to identify the next instruction to be executed. Then there are certain values need to be loaded when it starts execution again. So we need the CPU registers, and how that particular process was scheduled will be available in the scheduling information, because sometimes when a process terminates, or process state changes from running to ready, or running to wait, then certain information has to be saved. For example, the timestamp it stopped running, last time that it used the CPU or the processor. So like that, certain scheduling information is required. Then the memory management. So amount of memory allocated, amount of memory used, and certain variables and their values need to be stored. And the accounting information. So who are the owners for this particular process? That means the application and the users who executed this program. And then the input output status. So what is so how many files are allocated to this, and what is the original storage location for this particular application. So like that, the input output status will be also saved in the process control block. So in a diagram we can show the components for a process control block. We save the process state, process number, and the program counter, then the register values, memory limits. So how much memory is allocated, what is the address space allocated for it, and then how many files are associated with this process, and the global variables, temporary variables. So those values will be also saved in the process control block. So the process will have a process control blocks if there are several processes at the moment executing in different states. uh, until it terminates, it will maintain a process control block. So at a given time, a CPU can switch from one process to another process. There are several scenarios that we will discuss why switching is required. So um, so for now we will assume that we have process 0 and process 1 denoted by P0 and P1. So initially P1 is executing and using the CPU, and then it will stop its execution for a particular reason. For example, it requires certain input output operations, so it can stop. So when it uh, stops execution, what happens is the state of the P0 should be saved, and you can see it is saved on the PCB0, that is the process control block associated with P0. So it will save the state including the next instruction to be executed, its variables, temporary global variables, and all the necessary information, scheduling information, and the memory allocation, memory addresses, those will be saved. Then the CPU won't be idle when P0 is stopped. So then CPU will load another process that is available in the ready queue. So we will assume that is P1. So to load P1, then the necessary details to run P1 or execute P1 should be considered. So we load the state of P1 from PCB1, that is the related or associated process control block for P1. So then it will start its execution. So you can see in between saving the details of P0 into PCB0 and loading the data from PCB1 takes some time, maybe a very small time in milliseconds or maybe nanoseconds, but still there's a small idle time. Sometimes this is negligible time that the user does not notice any delay. So but there's a idle time, even though it is small, there's a idle time. So then P1 will start its execution. After a while P1 will also stop. So when P1 stops execution, then P1 state should be saved in the PCB1, and then the CPU will switch back to P0. Then we need to load the necessary information from PCB0. So that is how, when processors switch from one another, the state will be saved and the new process state will be loaded, and then it can execute. So in between saving and loading, there's a small idle time for the CPU. So processors are scheduled in different ways in operating systems using different data structures. We call them as queues. So the first queue, that is job queue. So job queue is called as long-term scheduling. Why? Because when we consider all the applications available inside the operating system, it maintains the number of processes or programs to be executed. So those are available in the job queue. So a job queue is a long-term scheduler because it has all the necessary programs that can be executed in the operating system. Then the ready queue is the short-term scheduler, where when a particular process is ready to execute, that particular process will be brought into the ready queue. So ready queue will be managed by the operating system, and the processes that are on the ready queue will be available on the main memory and waiting for its time for execution. And then we have a device queue. So each device will have its own controller as well as certain buffer space or memory. So that we have discussed in the first chapter as well. So when there are multiple processors waiting for input-output operations, then those processors or jobs will be loaded into the device queue, will be managed by the device controller. So a process can migrate in these different types of queues based on the different requirements. So when we consider the ready queue, that is the short-term scheduler, so ready queue will be directly available for the CPU, because from the ready queue we select the next process for the execution. So a CPU can use, or CPU can give a chance to a process for its execution, and it can stop its execution based on different situations. So for an example, when there's input output request, then the CPU will stop the current process. Why? Because then that particular process does not need the CPU for execution, because it has certain input output operations. For example, I want to save the file, or I want to copy the data from one file to another file, or I want to take a printout. So those are input output operations. So based on that, the CPU will stop its execution. So you can see the first scenario or the first situation that we consider is input output request, then it goes to the input output queue or the device queue. And when that particular task is completed, then that particular process will be again put back into the ready queue. So that is the first scenario. The second scenario is the time slice expired situation. So what is this time slice expired uh, condition? So a CPU will have certain scheduling algorithms. For an example, certain scheduling algorithms will continue until that particular process completes its task, and certain scheduling algorithms will have a time slice. That means it will stop execution for a particular process in a given period of time. So normally this happens in milliseconds. For examples, we can set a particular time slice for 8 milliseconds or 16 milliseconds. So each 8 milliseconds the CPU will stop its execution and load a new process taking from the ready queue. So when that particular time period is over, that process will be taken out from the CPU. So that means it will stop the current execution and give a chance to the next available process in the ready queue. So when that happens, that process that stops its execution will be considered as expired. So it will be again put back into the ready queue. So that is the second scenario. Third scenario, so a process can create another sub process. We call it as a child process. So then the CPU will stop its execution because it requires another task, that is creating another process. When that process is executed, then it will be put back into the ready queue. So the fourth condition is waiting for an interrupt. So a CPU will take a process out or stop its execution when a particular task is occurred. So it will wait for the interrupt. When the interrupt occurs, then again it will be put back into the ready queue. So those are the four conditions that a particular process will stop its execution and put back again into the ready queue. So that is how the ready queue is managed when it is considered the process scheduling. So this happens very quickly. In most of the time this happens in nanoseconds, or sometimes it can be in milliseconds as well. So schedulers can be categorized like this: long-term scheduler and the short-term scheduler. So the long-term scheduler is the job scheduler. That means it will consider all the available processes according to the available programs inside the operating system. When a program is ready for execution, it will bring that particular process into the ready queue. So ready queue should act very fast. So then it becomes the short-term scheduler. So in addition to the short-term scheduler and the medium-term scheduler, there's another type of a scheduler that is called as medium-term scheduler. So at the first chapter, I explained about virtual memory management. So that means the available main memory is not enough to manage all the processes inside the main memory. So therefore we need extra space in the storage, where it should be faster and also easy to load the necessary executable code segments into the main memory, and then we need to take out certain unwanted instructions available in the main memory. So when we remove certain unwanted instructions or processes in the main memory, we call it as swap out. And when we load from the virtual memory to the main memory, we call it as swap in. So the medium term scheduler is based on swap in and swap out from the secondary storage, and this particular mechanism also requires certain scheduling. So we call it as the medium scheduler. So this particular scheduling will be available as two stages. That is when a particular process terminates, or process does not require immediate execution, then it will be taken out and put it back to the virtual memory, and certain processes which needs immediate execution will be swap in from the virtual memory to the main memory, and those processes will be available in the ready queue. So this swapping swap out also may go in for several cycles to complete a set of processes. So up to now we have discussed about the short-term scheduler. So normally it happens in nanoseconds or milliseconds, so it's very fast. So the short-term scheduler maintains the CPU and the ready queue. Long-term scheduler is available for all the available programs which can be executed. So it's a long-term scheduler. Normally the time frame for long-term scheduler will be measured in seconds or minutes. So the long-term scheduler will control the degree of multi-programming, that it has all the programs which needs can be converted into processors, and the short-term scheduler will identify the degree of multitasking. So how many tasks can be executed parallelly in a given computer system. So when we consider different types of processors, some processors are IO bound processors. That means it spends more time in input output operations, so it requires shorter CPU usage. We call it as short CPU bursts, because most of the time it is doing or happening input output operations. CPU bound processors, on the other hand, will spend more time executing or using the CPU, so it may consider very long CPU bursts, very long CPU usage. So another important aspect of process management is called as context switch. So a context switch means when one process terminates its execution, or using the usage of the CPU, and loading another process from the ready queue into the CPU. So this particular switching of processors is called as the context switch. So how does this context switch happens? So when a particular process terminates, then that particular process needs to save its state in the process control block, and then the new process needs to be executed. Then that particular process and its state should be loaded for the execution. So for that particular process is also actually a process switching. We call it as context switch. So it requires number of tasks, and so that will also take certain amount of time that we have discussed in the previous example, when a process stops and a new process uses the CPU. So the time is depending on the hardware support available in the computer system for context switching. So a particular process can create certain sub-processors for a particular task. So we call it as a child process. So for an example, let's assume that we execute the word processor, and when we execute the word processor, there are certain additional tasks available as well. For an example, let's say the spell checker, the input output taking from the keyboard, format the document. So from the parent process, that is to run the word processor, there can be child processors created for each task. For example, for word process spell checking, we can create a child process. Formatting, we can create a child process. To take the keyboard input, we can create a child process. So each process sometimes can create several child processors. So all will be managed by the or linked to the parent process. So it will create a process tree. So each of these processes are also given a unique process identifier. So sometimes certain resources will be shared by parents process and all the child processes in some situations. So for an example, the same document will be used, and sometimes same memory slot or the memory space will be used by parent and the child processors. Sometimes the child processors will share a subset of parent resources. For an example, parent process will have a particular amount of memory space, so the child process can share part of the parent allocated resources or allocated memory from the parent. And sometimes the parent and the child processors does not share any resource. Now for an example, if a particular file is being linked to another file, if that is handled by the child process, so the child will handle that particular process that is linked, and parent does not have any shared resources. So that is how the resources are shared between parent and child processors. And then about execution, parent process and the child processors can execute concurrently. That is the common way of program execution in the operating system. And then in certain situations, parent have to wait until the child process completes. Now for an example, if the user wants to save the document, then it creates another child process to save the document, and without saving, the parent process cannot terminate. So it has to wait until the child process completes, then the parent can terminate. So address space, sometimes the child and the parent can share, or the child process can duplicate the parent's address space. And sometimes the child process can share the parent's address space as well, so the necessary instructions will be loaded separately, as well as can be shared in the same memory. So creating a child and creating the parent process is identified differently by different operating systems. So these are some examples. Fork and exec, they are two different system calls which are available in the Unix or Linux operating systems to create processors and child processors or subprocessors. So this is how a child process is created. So first the parent is created, and then we can create the child processor. Without a parent process, we cannot create, or the operating system cannot create a child process. sometimes a single parent process can create multiple child processes as well. So the parent and the child process, as I explained earlier, can share, or it will be separately using the resources such as the memory, file, input output devices, and all the other available resources inside the operating system. So when a child process exits, then the parent can start its execution, or the parent process can terminate. So it depends on the situation and the task assigned for a particular child process. So for an example, as I explained earlier, saving a file. So until the file is saved, the parent process cannot complete, so it has to wait. So when the child process completes its execution, it can call the exit function, then the parent can start its execution, or it can also terminate. So process termination is vital because abnormal termination of child and parent processes might give a lot of failures or errors to an operating system. So what is process termination? When a process executes its last instruction, then it will indicate the operating system that it has already completed its task, and then it can exit. So what happens when a process terminates? It will release all the resources allocated for each process. That means memory, input output devices, associated files, registers, and the other available resources. It will release all the resources, and it can terminate. So when a particular child is not terminated, then the parent has to wait until that particular child completes its task. Sometimes a child and parent can terminate together. So if the resources are allocated separately, and if there are no updates to be happening to the parent process, so the child and the parent can terminate at the same time. So a particular process can terminate successfully or unsuccessfully. So that means when a particular task fails, that particular process can terminate, or when a that particular task is complete successfully and terminate. So whether it is the child process or the parent process, when it terminates, it has to deallocate all the resources that are assigned for that particular process. So if a particular task assigned to a child is no longer required, then that particular child process can terminate. So if the parent is existing, then the child process needs to complete its execution, and when the child process completes and notifies the parent, then parent can terminate. So sometimes a particular parent process will have multiple child processes. So in that case, the parent will wait until all the child processes are terminated. So we call it as cascading termination. So in a given instance of an operating system, there will be multiple processes ready for execution, and some processes will be executing at that particular point of time. So when we consider an individual process, a process can be independent or cooperative. So an independent process does not share information with any other process, does not share any resource with any other process. It will start its execution on its own and terminates the execution uh, on its own. So it's a independent process. But many of the processes in modern operating systems, those are cooperating processes. That means once one particular process output will be taken as another processor's input. So sometimes it shares certain variables, it shares certain data. So many processors are acting as cooperating processes. So this particular mechanism of cooperating processes, if one particular process fails, it might affect many other processes. So that is one particular problem in this cooperating processes. But anyway, in modern operating systems, most of the processes are cooperating processes. So why we need the cooperating processes? Because we can share the available resources, information among the processors. So it will reduce the time for execution, and it will be more effective, and accurate results can be obtained as well. And also we can maintain modular-wise components inside the operating system. So one particular output will be a input for another process, and in that sense it will be more convenient as well. So cooperating processes needs to communicate each other, so we call it as interprocess communication. So in operating systems, this interprocess communication happens in two models, that is shared memory and message passing. So message passing can be indicated like this. So each process will have its own space for messages. So if process A wants to pass the particular message, that means, for example, let's say some variables, so it will be passed from process A to the kernel, and then from the kernel to the process B. So that is the mechanism. Directly a process cannot send messages or can send any content from one process to the other process, so it will go through the kernel in message passing. But in shared memory, what the process can do is it can update the shared variable, then and the other process can load the value of the shared variable. So in memory in message passing, it might create a delay, but it is much safer because it comes through the kernel, that is the privilege mode. But in shared memory it is easier, faster, but it may not be the most secured way of doing it.